All right, hello, this is Professor Bond. I thought that I would start out with um, something that's pretty interesting. This is a proof of the Pythagorean theorem. Um, so, whether you remember the name or not, this is something most of you have probably seen already, but let's go over it. So, it's the theorem about right triangles, the lengths of the right triangles. So, the Pythagorean theorem itself says that if you have this right triangle, that just means that two of the sides, which we call legs, form a right angle. So you put one on the ground, the other one goes straight up like a flagpole. It doesn't lean left or right like the Leaning Tower of Pisa. It's nice and straight. Got the other one is the hypotenuse. Well, you got two legs in the hypotenuse. And is there some relationship? Is there anything special about 90 degrees? And it turns out 90 degrees is very, very nice. Well, if A and B are the lengths of the legs of a right triangle, and C is the length of the hypotenuse, then A squared plus B squared is equal to C squared. So that's very nice. But what we're going to do here is I'm actually going to show you a proof of the Pythagorean theorem. So you will not be required to recreate this proof at any time. It's a nice party trick. It's not immediately obvious why it should be true just by looking at it, but once you have one idea and a little bit of trigonometry and algebra to put the pieces together, it's pretty cool. There are a lot of proofs that are really hard, but this one, you just need the right idea. And so I've actually got an outline, the main idea that's going to make this proof work. I'm going to sort of unveil it like a sculpture by Michelangelo or something. It's just pretty neat. So what you might want to do is, after I show you the picture, you might want to pause the video and sort of mess around with the algebra. It's totally optional, but if you're feeling motivated or curious, it's a neat picture. I'll just show you the picture, and I'll show you one main idea, something that you want to think about. What's the insight? What do you do with this picture? And if you can work out the details, then that's really cool. But don't feel bad either way. But anyways, here it is. So what we do here? Here's in the bottom left, we have one copy of the right triangle with side lengths A, B, and C, and we just sort of rotate it 90 degrees. So these are lying along a straight line, and then we got this right angle here, and then there's the other leg of the second copy. So what we've got is the big picture is we have this giant square, and it has a certain length, and it's got a certain width. Well, both of those are A plus B. So the entire figure, you can compute the area one way. So there's one way of looking at it, and the area of this big rectangle, which is actually in this case a square, is you have A plus B times A plus B. Well, there's another way you can find the area, so you might want to think about that. There's actually 4 triangles and a square. So this would be a really cool time to pause the video if this seems interesting to you and you want to if you want to compute the same things 2 different ways. Well, that's where an equal sign comes from. You do one thing, then they both represent the same whole. Some stuff cancels out, and I claim that this is what you're going to get. But there's one more insight you might want to worry about, and that is that this thing in the middle, well, it's some kind of figure with 4 sides. It's a quadrilateral, quad for 4. But is it really a square? And it turns out, actually, yes. This is always the way I drew it. I did the best I could with a ruler. But my hand's a little wobbly. There's the thickness of the marker that kind of is a little bit tricky to make everything line up quite perfectly. But if it were drawn, absolutely perfect, those would be right angles. And this is not a trigonometry course, I don't want to stress over this too much, but you have side A, and you call this angle 1. It's the one that's not the right angle that's on side A, and then this one is angle 2. Then there's a fact of trigonometry that says 3 angles add up to 100. The 3 angles of a triangle add up to 180 degrees, but then these 3 angles add up to 180 degrees. So what's missing? If these 1, 2, 3 is what you need to get 180, and you have 1, 2, well, there's the third one that you need. Or rather you have, well, okay, this triangle and this triangle. Side A is next to angle 1, side B has this angle 2, and then, okay, there's 1, 2 with 90 left over, and then there's these 2 angles with 90 left over, because the angles of a triangle add up to 180 degrees, and the fact that this is a straight line cut into 3 segments, the 3 smaller angles also add up to 180 degrees. So 180 means you go from one direction to its opposite. So every time you have the angle that's opposite to B, angle 1, then you've got the angle 2 here, because that's the angle that's opposite of A, and it's the same picture over and over again. So angle 1, angle 2, and then once you've got angle 1 and angle 2, you know that you've got exactly this 90 degrees left over. So that's pretty cool. That's something that's the one insight that you need. So now that that's that one consideration you have to take care of, but now you know the center figure is a square. Now you can start shading. So if I shade this as a red area, and so now that I've said a little bit more, so there are 2 different things that represent the total area, and one is it's never too late to pause if you want to think some more. I haven't told you the whole story yet. One is conceptually just the big square that encompasses everything all in one shot. So area of the big square these, well, I colored those 4 right triangles that are colored in red. In right triangles, it's the area is just 1/2 base times height, and then I'll call it the middle square. So not the big square, but the thing that I've colored in blue. So on the very far outside, the big square is kind of, that has a black outline. The 4 triangles are in red. The square in the middle is in blue. So yeah, but now let's just do it. So I've given you lots of opportunities to pause if you want to write this all up. Kind of running out of space, but the left-hand side, the big square is, let's just call this number 1. Let's call this number 2. Well, what's the area of the big square? That's it's a rectangle, so it's just A plus B is the base times height. And I'm going to do this one a little bit fast. We will review this as a separate lecture because it's really important. Some of you might already be really good at this. I don't want to take anything for granted, but you do get a squared plus ab plus another ab plus b squared. So one of your homework assignments is going to be just a review of multiplying out things exactly like this, and we'll slow it down and do it in detail. Right now it's not the emphasis. So on the one hand, that's the total area of the big square. And for number 2, what do we get for that? I'm gonna have to erase a little bit, but I think this is just saying in words what the picture already says for us. So I kind of miss the big classrooms with the big dry erase boards, but we're staying as safe as we can here. So just bear with me here, and let's do it. So number 2, we have 4 copies of. It's a right triangle, so make sure if it's not a right angle, you have to figure out the height, which might be really obnoxious trigonometry. But for a right angle, it's convenient because it's just the base and the height. This side of the triangle is already pointing exactly in the same. It already tells you the height because it's not leaning sideways, which makes it shorter and closer to the ground. It's straight up, so that's cool. So I shaded the inside of this red, so it's a triangle. So it's only half. A triangle is literally like a rectangle that's been cut along the diagonal, so you get 2 equal halves. One of them is the actual triangle itself, and then there's this, where does that one half come from? Or there's another, if it were a rectangle, you'd have this other half. So the triangles are only half of a rectangle. And we had to work pretty hard because just any old random quadrilateral, it would have to be base. It would have to be like some kind of base times height type of thing. But we know that they're all right angles, so it's actually a rectangle. So it's all. So we only have 1 copy of base times height. So the triangle area equals 1/2 times base times height. All right, so the same calling number 2, total area. Well, we've broken it into 4 parts, 4 copies of the 4 identical, sort of rotated identical copies of the same triangle, plus the square that's in the middle. So the middle is the square in the middle. I'll just call it a rectangle. The same rules apply as if it were just an ordinary rectangle. Area of rectangle. Base times height, but you do not have to divide by 2 because dividing by 2 would mean you cut it in half to get 2 equal triangles. So we've got 4 times a half. So 4 halves is just, the first one is 2ab, because the 4 and the 1/2 multiply to get you just 2, and then so this was, these are the pieces we put together. So number 1 is that we've got 2 ways of writing the same thing. so the sort of the conclusion is we have 1 is equal to 2, which is a squared plus 2ab plus b squared is equal to 2ab plus c squared. And anytime two things are equal, you remove the same thing from both sides. You get a new expression, two new expressions that are also equal to each other, which is exactly this. A squared plus b squared is equal to c squared. So really the only technicality is convincing yourself that this figure in the middle really is really does have right angles. But once you have the right picture in mind, the rest is a lot easier than just getting the right inspiration in the first place. So I think that's pretty neat. It's something that you should probably see at least once. Take a little bit of effort to understand it, but in ancient Greek times, they didn't really think about it algebraically. They kind of tended to think about things like in like sentences. They didn't quite have the notation that we have is a little bit more streamlined than what they had back in ancient times. So it was always a little bit harder for them to figure stuff out because we've had thousands of years to think about it and from new perspectives. And here, just a little bit of algebra goes a pretty long way to just sort of give it to you like almost immediately, and that's pretty cool. So we'll be what we want to take home from this in this particular course is we're going to use this when we talk about the distance formula, and that's just literally how far apart are like two corners of a right triangle. So you just go in it. You can always travel horizontally and then vertically in a 2-coordinate XY plane. And then, well, how far is the distance? That's represented by the quantity c. So it's literally the same thing, just sort of coordinatize. You put coordinates on everything, and you put everything together, and you get this thing that's called the distance formula. That's what we'll do with it in the near future. All right, so that's that. Hope that was interesting. All right, good stuff.